Hello everyone, I am Dr. Sonia Juneja, Assistant Professor in Kite Group of Institutions, Ghaziabad. Today my topic is Poynting Vector and Poynting Theorem, which includes Poynting Theorem, Derivation of Poynting Theorem, Physical Interpretation and then example. What is Poynting Vector? The rate of energy flow per unit area of an electromagnetic wave traveling from one point to another point in space is denoted by a vector which is known as Poynting vector. When electromagnetic wave travels from one point to another point, it transports energy in terms of electric and magnetic field from one point to another point. The rate of energy flow per unit area is denoted by a vector which is known as Poynting vector. Means Poynting vector is rate of energy flow means power per unit area. Rate of energy flow means power per unit area is denoted by a vector when EM wave travels from one point to another point in a space. Then it transport energy, it transport power in terms of electric field and magnetic field. This power per unit area or rate of energy flow per unit area is denoted by a vector which is known as Poynting vector and denoted by vector S. Vector S is equal to E cross H. E cross H means the direction of S is perpendicular to both vector E and H. Vector E and vector H means the direction of propagation. Means the direction of propagation is the direction of Poynting vector. Means electromagnetic wave is a wave which consists of electric field vector and magnetic field vector. Both are perpendicular and also perpendicular to the direction of propagation of wave. S is equal to E cross H means the direction of S is perpendicular to both E and H means the direction of propagation, and the unit of Poynting vector is watt per meter square. Power per unit area, watt per meter square. Then Poynting theorem. To derive the Poynting theorem, we know that Maxwell third and fourth equations are, Maxwell third equation is del cross E or curl of E is equal to minus del B over del T. B is equal to mu H, therefore curl of E is equal to minus mu del H over del T. Then del cross H or curl of H is equal to J plus del D over del T. D is equal to epsilon E, therefore curl of H is equal to J plus epsilon del E over del T. This is the Maxwell fourth equation. Third equation is curl of E is equal to minus mu del H over del T, and fourth equation is curl of H is equal to J plus epsilon del E over del T, where mu and epsilon are the magnetic permeability and electric permittivity of the medium. Taking dot product by vector H in this equation, taking dot product by vector E in this equation, then we have H dot del cross E. H dot del cross E is equal to minus mu H dot del H over del T, minus mu H dot del H over del T. Taking dot product by vector E in this equation, then we have E dot del cross H is equal to E dot J plus E dot del D over del T, where D is the electric displacement vector which is equal to epsilon E. Then E dot del cross H is equal to E dot J plus epsilon E dot del E over del T. Subtract these two equations, then we have H dot del cross E minus E dot del cross H, which is equal to minus mu H dot del H over del T minus E dot J minus epsilon del E over del T. Then using vector identity, H dot del cross E minus E dot del cross H is equal to del dot E cross H. Using vector identity, del dot E cross H is equal to H dot del cross E minus E dot del cross H. Then left hand side becomes del dot E cross H minus mu H dot del H over del T minus E dot J minus epsilon E dot del E over del T. Now del by del T of E dot T, dot product of two vectors. First E, then del E over del T dot del E over del T plus E dot del E over del T. Del by del T of E dot T is equal to E dot del E over del T plus E dot del E over del T. Means it is equal to twice of E dot del E over del T. E dot E becomes E square. Then E dot del E over del T becomes 1 by 2 del by del T of E square. Similarly, if E dot del E over del T is equal to half of del by del T of E square, then H dot del H over del T is equal to 1 by 2 del by del T of H square. E dot del E over del T is equal to 1 by 2 del by del T of E square, and H dot del H over del T is equal to 1 by 2 del by del T of H square. Substituting H dot del H over del T and E dot del E over del T in this equation, we have del dot E cross H is equal to minus mu 1 by 2 del by del T of H square minus E dot J minus epsilon 1 by 2 del by del T of E square, which implies del dot E cross H is equal to E minus E dot J minus del by del T of half epsilon E square plus half mu H square. Del dot E cross H is equal to minus E dot J minus del by del T of half epsilon E square plus half mu H square, where half epsilon E square is the energy stored in electric field and half mu H square denotes the energy stored in magnetic field. Half epsilon E square is the energy stored in electric field and half mu H square is the energy stored in magnetic field. Then integrating this equation del dot E cross H is equal to minus E dot J minus del by del T of half epsilon E square plus half mu H square. Integrating this equation over the volume V, then we have volume integration of del dot E cross H into dV is equal to minus volume integration of E dot J into dV minus volume integration of del by del T of half epsilon E square plus half mu H square into dV. When we integrate this equation over the volume V, then we have volume integration of del dot E cross H into dV is equal to minus volume integration of E dot J into dV minus volume integration of del by del T of half epsilon E square plus half mu H square into dV. Applying Gauss divergence theorem on the left hand side part, then this volume integral is converted into surface integral. Then we have surface integration of E cross H dot ds, which is equal to minus volume integral of E dot J into dV minus volume integration of del by del T of half epsilon E square plus half mu H square into dV. Then volume integration of E dot J into dV is equal to minus surface integration of E cross H into ds minus volume integration of del by del T of half epsilon E square plus half mu H square into dV. This is the required expression for the Poynting theorem. Now the physical interpretation. In this term, this expression, the left hand side, in this term, the first term of the left hand side is volume integration of E dot J into dV. This equation, E dot J into dV, this term represents the power dissipation of work done per unit volume. It means power per unit volume, because E dot J is equal to VI by D into A, means power per unit volume. When work will be done, then power dissipation occurs, means this term denotes the power dissipation per unit volume. And the second term of right hand side is volume integration of del by del T of half epsilon E square plus half mu H square into dV, which denotes because minus sign occurs in front of this term. Therefore, it denotes the rate of decrease of stored energy in electromagnetic field. Because this is the stored energy in electric field, this is the stored energy in magnetic field, and the sum of stored energy in electromagnetic field. And del by del T denotes the rate of change of stored energy in electromagnetic field, and minus sign denotes the rate of decrease of stored energy in electromagnetic field. And the first term of right hand side is surface integration of E cross H dot ds, which represents the rate of energy flow per unit area, which denotes the rate of energy flow means power per unit area, which is known as Poynting vector. And the unit of Poynting vector, we know that watt per meter square, and the direction of Poynting vector is direction of propagation of wave. Poynting theorem is also called work energy theorem because work done by the electric and magnetic fields on the charges, work done denoted by this term, because the work done by the electric and magnetic field on the charges within a volume must match the rate of decrease of energy of the fields within the volume and the net flow of energy into the volume. This is also called work energy theorem because this work done is equal to the rate of decrease of energy and the net flow of energy into the volume. This is the Poynting theorem. Now example. Considering that all the energy from a 1000-watt lamp is radiated uniformly, calculate the average value of the intensity of electric field of radiation at a distance of 2 meters from the lamp. In this numerical, we have to calculate average value of electric field intensity. In this numerical, we have power is equal to 1000 watt, distance is equal to 2 meter. Then we know that Poynting vector is equal to power per unit area. Then Poynting vector becomes 1000 divided by 4 pi r square, which is equal to 50.24 watt per meter square. Poynting vector is power per unit area, substituting the value of power and the area 4 pi r square, substituting the value of r here. Then we have Poynting vector 50.2 r watt per meter square. Then we also know that the relation between E and H, E by H is equal to 376.6 ohm. Solving these two equations, we have a value of E is equal to 86.59 volt per meter. One equation is S is equal to EH. From this equation, S becomes 50.24 watt per meter square. And second equation is E by H is equal to 376.6 ohm. Solving these two equations, we have a value of E which is equal to 86.59 volt per meter. Thank you so much. If you have any query, kindly mail me at sonia.juneja@kite.edu.